Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to tonight's Contemporary Science program. Our guest is Tulika Bose, Assistant Professor of Physics at Boston University and a member of the great international team of scientists preparing for the reboot of the Large Hadron Collider at CERN in 2015. Dr. Bose received her Ph.D. in experimental high-energy physics from Columbia University in 2006. Her postdoctoral research at Brown University focused on direct searches for new phenomena at the D0 experiment at the Fermilab Tevatron and at the compact Muon Solenoid CMS experiment at the CERN Large Hadron Collider. Both of these she will discuss tonight. She's also worked extensively on trigger and data acquisition for both the D0 and for the CMS and is currently serving as the trigger coordinator at the CMS experiment, another task she'll explain tonight. Dr. Bose has received already in her career a number of prestigious awards, including the Fermilab 2014 CMS Distinguished Researcher Award and a 2012 Alfred P. Sloan Research Fellowship awarded to the most promising of young scientists. She's produced numerous publications in ranking journals and is actively involved in searches for new physics using data collected by the CMS. It is a very great pleasure to welcome Dr. Bose. Welcome.
Thank you.
Okay, let's start. If you would give us a little background on the LHC in general, catch us up, so to speak. First of all, then why is such a massive machine, the biggest, I think, in history, necessary to collide little tiny things?
Okay, so I'd actually like to start with an analogy. Suppose you were interested, you have a nice watch and you want to see what's inside. You want to understand how it works. You get a screwdriver out, you open it up and you look inside. Okay, we want to look inside atoms. Mm-hmm. What are these subatomic particles? However, there is no screwdriver in this world that's going to open it up and show you what's inside. So we need tools, and our tool as particle physicists is a collider. Now here you may wonder, okay, how about I collide two ping pong balls? You know, they're just going to bounce off each other. What do you learn? However, what we observe at the LHC is something actually different. Rather, that we collide protons with protons, and when these protons collide, they disintegrate, and in the mess that comes out, there are a whole bunch of new particles. And it's somewhat similar to colliding your ping pong balls, and out of it comes basketballs, baseballs, footballs. All sorts of wonderful things come out of it. And so in this mess that's coming out, we see essentially the energy of the collision, that is, that what went in coming out as mass. So this takes us to Einstein's famous equation, E is equal to mc squared. The more energy you put in, the more mass you can create. Now, the particles we're interested in are so very, very rare that you really need, again, a lot of energy to be able to increase the probability of finding a rare particle. And so we try to push higher and higher in energy such that we can discover new particles that have not been discovered so far.
Okay, so and that's the only way to get at these particles. Is that it?
I mean, this is one of the ways, right?
Yeah.
The other way you could think of is this is like a big hammer. You're trying to get something out. The other way of looking at something would be perhaps going lower in energy, but looking more closely, doing precision measurements and observing what comes out of it. So in that case, you don't need to go for a very massive machine. You could have a smaller machine, but you're doing a different kind of physics.
Okay, all right. does it matter what kinds of particles you're colliding here?
Yes, it matters in the sense that how much energy is available for the collisions is determined by, are you colliding, two electrons with each other, or are you colliding an electron with a proton? A proton is not an elementary particle, unlike an electron. A proton consists of 3 quarks. And so a collision between an electron and a proton is different between an electron and a proton and a proton. And what we also do at the LHC, for example, is collide ions, lead ions with protons, etc. So what we have found is the kind of physics we want to do, the kind of energies we want to push, a proton-proton machine gives you access to a very large range in mass. And that was one of the design principles, therefore, for the LHC.
And then you have these different projects or at there, like the CMS and ALICE and so on. What's the purpose of these?
All right. So there are 4 major projects or detectors or experiments at the LHC. And one of them is called LHCb, which is really studying the physics of B quarks, and hence the name LHCb. And this is a sort of dedicated experiment looking at a very particular kind of physics. The other experiment is called ALICE, which studies heavy ions. So they are not so much interested in proton-proton collisions. They want to see what happens in heavy ion collisions to understand, for example, plasmas, or what happens right after the Big Bang in that sort of hot, dense material. The other 2 experiments are CMS, Compact Muon Solenoid Experiment, and ATLAS. These are 2 somewhat general purpose experiments in the sense that they do a wide variety of particle physics, including heavy ion physics, including B quark physics. But the main emphasis of these experiments has been, over the last few years, search for the so-called Higgs boson, search for new particles. And here the 2 experiments have the same sort of physics in mind, but they were built with different technology. And that is why 2 experiments were created, so you could go after the same physics but with different technology, because to begin with, we didn't know that both of them would work so wonderfully well. So this way, we had everything covered.
Yes, that's a wonderful, happy surprise.
Absolutely.
Yes, right. Now, in terms of the great accomplishment of 2012 of confirming the Higgs, what does that signify in general? Also, in terms of the implications for future research, those 2 things. What about the Higgs?
Right. I think, again, I'd like to start with an analogy to sort of first talk about, what is it? What is the Higgs boson? Right. So what I find useful, I'm going to borrow from actually a set of cartoons that were written by David Miller from UCL London. The UK science minister put out a challenge asking for cartoons or anything to explain the Higgs mechanism. And the prize was going to be a bottle of champagne. So David Miller went and he came up with these set of cartoons, and they're beautiful because you can really explain it in just 3 cartoons. So imagine you have a room full of people. They're at a party, a cocktail party, and a very famous person comes in through the door. And as the person walks in, people start clustering around this famous person because they want to talk to him or her. And the person wants to go to the other end of the room, but they're unable to go because they're being stopped by these groups of people. So it's almost as if that the fact that they are going more and more slowly seems like they have acquired more mass. Massive particles travel slowly. Here, this person is being stopped and is not going. So they're interacting more with the people, as a result of which they seem to have acquired mass. So higher the interaction, larger the mass. On the other hand, if a completely or relatively unknown person walks in, nobody wants to talk to them. They can go from one end of the room to the other. No interaction, no mass. They don't seem to have it stopped at all. So this was the idea that those people in the room is this Higgs field. And how a particle interacts with the Higgs field determines its mass. If it does not interact, it's massless. If it interacts, it's got mass. How much it interacts determines how heavy its mass is. Now, this is the Higgs field, but we talk about a Higgs boson. Now, what's the Higgs boson? Now, going back to our original room where people partying, suppose somebody puts their head in and they start a rumor. Now, they're not actually coming into the room, but the fact that people near the door have heard this rumor, they start talking about it. Then this goes on to the central part of the room and then to the other part of the room. So again, there is a clump or a mass of people who are passing this rumor along. So this sort of a clump in this Higgs field is the Higgs boson. And the fact that the Higgs field is there, you can only appreciate it if you find this clump or this particle, which is the Higgs boson. So for the last 50 years, we've been hunting to find this Higgs boson so that we can prove that the Higgs field therefore must exist and is responsible for giving mass to particles.
Is it also responsible for the differences in mass, assignment of mass to different particles?
Yes, again, yes. So depending on how a particle interacts, how much it interacts, will determine essentially what its mass is. And that's when we try to hunt for the Higgs. We try to hunt for the Higgs in different ways, in the sense that the Higgs can decay into different particles. And if we measure the Higgs and its properties in all of these different decays, we can sort of test its interaction with different kinds of particles. And herein comes the fact that the Standard Model, which is this it's an elegant set of equations which sort of describe all of particle physics. It has certain expectations for what the Higgs interactions with all of these particles should be. So what we are trying to do at the LHC is actually measure some of these properties of the Higgs. Now that we have found it, we've gone to the next step where we have started to measure its properties. Because what we want to identify is it the Standard Model Higgs? Or is it something else? Because if it's something else, then that means that there is another theory, which could be a simple extension of the Standard Model or something completely exotic. And that kind of a theory, for example, there is a popular theory called supersymmetry, which has 4 other kinds of Higgses. And these Higgses differ from this Standard Model Higgs in sometimes very, very small ways. So we need to measure the properties of this Higgs very, very precisely in order to be able to say, is it the Standard Model Higgs or is it perhaps a SUSY Higgs?
Right. And you do expect to be able to do that. I mean, you eventually,
so that's
which would really be a big deal for some of these people who've been working on supersymmetry for a long time.
Exactly,
right?
yes. So this is the big sort of goal for our next run, is exactly to go and measure very, very precisely the Higgs properties such that we can identify whether or not could it be a SUSY Higgs or is it actually the Standard Model Higgs.
Yes, that's fabulous that you can accomplish that finally, at last, because they've certainly waited long enough just even for the Higgs. Okay, a couple of things about the LHC just in general. It uses a lot of energy. That's one thing. And it produces a lot of data. So could we go to the energy first? Can you give us a clue here about this, where this energy is coming from to do this, and why it takes all this energy?
All right. So we start by accelerating protons. Now, protons are created from literally a bottle of hydrogen gas. You ionize, you produce protons. We accelerate them using a set of accelerators, and ultimately it gets into what's called the Large Hadron Collider. So we have a beam of protons going in one direction, another beam of protons going in the other direction, and they are made to collide at certain specific points, and those points are where the detectors are situated. Now, what is the energy of these protons? By these stepwise acceleration, back when we first started the LHC, the first part of the run 1, each proton had an energy of 3.5 TeV, or trillion electron volts. And so you had 3.5, the total energy of the collision that was available was 7 TeV. The following year, they increases a little bit. So you have 4 TeV colliding head-on with 4 TeV, and you had 8 TeV of center of mass energy. Next year, when we restart, this is going to increase even further, And the expectation is, the exact numbers are to be confirmed by the LHC, the expectation is we might have close to 6.5 TeV, 6.5 TeV, which gives us about 13 TeV for the center of mass energy. So this is almost double the energy that we had in run 1. So the kind of physics that we should have access to, it opens up an entire new regime, essentially.
Right. Is that the maximum TeV for the LHC?
So the design of the LHC was always 14 TeV.
Okay.
So they expect
so
that this is going to be close to the design,
yes,
13 to 14 TeV.
Right, which is amazing all by itself, right. Now, does this amount of energy sort of drain the communities around? Can you give us an idea of how much energy it takes?
Well, I mean, in terms of, every accelerator that you're doing, right, you have various steps, and you're trying to accelerate using technology, which of course is using power, which is coming from the region. And so it costs a lot.
Yes.
So for a long time, for example, CERN would actually not have the LHC running over the winter months, because the cost of running it, the power, was just prohibitive. You just couldn't do it. And they would run only during periods where at least this was manageable. So yes, it's a costly enterprise to do that.
Right.
And it is a drain on resources. But again, the technology is such that you're able to do it. I mean, 30 years ago, nobody had imagined that we would be able to have collisions at close to 14 TeV center of mass energy.
It does seem amazing, yes. The other thing then, just to get in quickly, is the helium that has to be cooled. Can you tell us about that? Why is that? And
right. So a big part of the LHC is magnets. And what do the magnets do? They are responsible for moving the protons in these circular paths. Any sort of particle in a sort of a magnetic field is going to bend, and these magnets provide that magnetic field. In order to have the kind of bending we want, these need to be very big magnets, providing high magnetic fields. That can be only done by superconducting magnets. Now, a superconductor is something which, below a certain temperature, essentially allows, a lot of current to go without any resistance. And in order to be in that sort of temperature, it needs to be kept cooled. And that's where the liquid helium comes in, because it allows essentially all of the superconducting technology that we use at the LHC to be kept at the kind of temperatures that we want. And because if they're not, then they can no longer be superconducting, and that means we no longer will be able to have the kind of bending that we need in order to make this work.
Okay. Now, I had seen somewhere that it is actually colder than space.
Interstellar space.
True?
That is very true. I mean, some of these facts are actually quite amazing.
Really, it's amazing that they can do it, produce
that's
that.
That's right. So, you have to be that cold. The kind of vacuum that you need to maintain is, again, like, on the moon or somewhere in the atmosphere in the universe. It's not something, it's other ways, repeatable on this earth.
Yeah, that's astounding. Now, another thing is the level of data, the amount of data that this is collecting. It must have people all over the world concerned about where to put this stuff. You gave me an idea of what this data, how big this data is. Tell us about it, please.
Right. So the data that we end up writing out in just sort of simple terms, if you were to pile sort of tapes or disks containing this data on top of each other, 1 year's worth of LHC data, they say, will rise up so high, it'll be higher than where the Concorde flies.
And that's 1 year.
That's 1 year. And this is the data we're collecting, not the data we are producing. Now, collisions at the LHC between these protons happen every sort of 25 nanoseconds. That means the rate we are talking about is 40 megahertz, or 40 million times a second. Okay, that's how quickly these collisions are happening. 40 megahertz. But the money we have for the kind of tapes and disks, etc., where we write out all of this to, allows us to write out data only at the order of a few hundred hertz. So we're going from the initial production after the collision at a rate of about 40 megahertz to only about a few hundred hertz.
So you have a selection process.
Absolutely. This selection we call as the trigger. This is the part that I work on.
Yes.
And the trigger runs online. That is, every 25 nanoseconds, it's looking at the data. It's making a very quick decision.
Wow.
Does this event look interesting to keep, or should I throw it away?
Yes.
And if it's interesting to keep, you keep it and you push it down the pipeline. If it's not interesting, you throw it away right away. And we have a complicated, it's a multi-tier trigger system which works with the kind of information and time. It's happening real time.
Yeah.
So you have initially the order of microseconds to make a decision. Then at the later on level, you may have maybe 100 milliseconds. And in this period of time, you have to decide that you're going to keep some amount of data. And keep in mind that the data that you're saying no to is literally going into the trash. You will never ever see it. So if you don't design your trigger well, all your Higgs or your new particles may be in the trash and you may not be writing it out. So you have to be very, very careful.
That's a huge responsibility. That would keep you up at night,
It
for
does
sure.
keep me
It
up
does
at
keep you up. And so let's go to this. This is where your work is centered. And so in this startup period, first of all, just that you have to be so very careful about that. Can you give us an idea of how you design this trigger stuff? Can it be made sensible to the layperson?
Okay. So at CMS, we actually have quite an exceptional trigger in the sense that we have what we call a two-level trigger system. The first level is essentially hardware and it's electronics, which is looking at all the events that come in, and it's making very coarse decisions, such as, does this event have a muon with a certain momentum? If it does, let's keep it. If I don't find anything interesting, let's throw it away. So we have to design and put into the hardware, into the electronics design, some of these algorithms which make very coarse decisions. Do I see an electron? Do I see a muon? Does it have certain momenta which I expect in interesting like particles such as a Higgs particle? So we use our current knowledge of physics and what we think it should be like to make some of these selection criteria. And this level 1 trigger has about a few microseconds to make a decision. It then decides and it gets this 40 megahertz down to about 100 kilohertz and it sends it to a farm of computers. These farm of computers now, because they get only about 100 kilohertz, they have a little bit more time. It's a little bit easier, 100 kilohertz versus 40 megahertz. So they run somewhat more complicated algorithms, and with those algorithms, again, they use more refined decisions, because now they can ask for not just an electron, but perhaps the charge of an electron, for example. So they can look at more characteristics, make more complicated decisions, and ultimately, whether the result of that, as long as the event has satisfied certain interesting criteria, we write it out, otherwise it gets thrown away. And going back to your earlier question, all of this that we are writing out is this huge amount of data.
This is the one that goes higher than the Concorde.
So if we were literally writing everything out, I mean, I can't even imagine
the
how.
Earth, exactly. You're not sure what you're going to find at this energy level this time around. I take it that you work on these algorithms very carefully, yes? Is it possible to sort of predict what you think you might find? You're looking for surprises, but it seems so scary with throwing out a lot of it. Yes?
No, that is the biggest challenge, right? That we have certain ideas, you know, from theory, from our own understanding, that okay, if this is going to be a particle, you know, for the Higgs, it was easier because the Higgs, you know, was predicted. We knew what sort of properties it had, so we could trigger on it or design algorithms to select it in an easier way. But this other new physics that could potentially be out there, we don't really know what it is going to be like. We might take certain guesses that, okay, we would expect that it would be typically high momenta, because if there's low momenta, then we should have actually seen it by now, or if it had a low mass. So the fact that we have not seen it makes us think that maybe this is a heavy massive particle, which will produce particles which have high momentum. So we use some common sense, some knowledge of theory, and our understanding of the world and how things work to design design these triggers.
Yeah.
But we have to keep an open mind because it could be something completely surprising.
Yeah.
And we don't want it to be thrown away.
Exactly.
So sometimes what we have is, well, some of these are very dedicated, exclusive triggers. We are looking for certain characteristics.
Yes.
At the same time, we design somewhat inclusive triggers, which may be more general, but we write out only a small amount of those, with the hope that if new physics were to come in this sort of a category, we might see a hint, and then we can go and redesign our trigger strategy to start to focus on that.
Right. Do the different experiments like ALICE and CMS and so on, do they have different triggers?
Yes.
Okay, so that might...
So that again, I mean,
Yeah.
our experiments, because they're built differently,
Yeah.
our triggering is different.
Yeah.
CMS I talked about has a 2-level
Yeah,
trigger system.
right.
Atlas has a different system which does it in 3 ways. Now, certain things are common, and we're essentially
right,
triggering
right,
on the same
right.
kind of physics and known physics. But yes, you could, if we don't do a good job, it's possible that, one experiment sees it and the other
I was
experiment
just going to
doesn't.
say it's another way, and then at the same time you're overlapping in important
Right.
regards so that you can check,
Exactly.
confirm things.
That
Right.
if both experiments, because they're so similar, if you were to find something in new physics in a way you would expect that the other experiment would also see that signal, maybe not to the same intensity, but still see something.
Yeah.
So it's a very good cross-check
Right.
to have another sort of answer.
Right. Tell us some of the things you think might be out there that you're looking for this time.
Yes, there is a whole slew. I mean, that's what's most exciting.
Stuff they've been looking for and stuff they...
Exactly.
Yeah.
So, so I would say, broadly speaking, there are sort of 2 main sort of new physics we're looking at. One is this model which has been around a long time, which we refer to as supersymmetry, which essentially predicts that for every standard model particle, there is a partner particle. And it helps to solve some of what we call things we don't understand about the standard model. One other thing it helps to do is the fact that, what we understand the universe today is really about 5% of the visible universe. And a large fraction of this is what we call dark matter, which we can't really see. We can only infer its presence from its gravitational interactions. Now, supersymmetry is good in the sense that it actually has a candidate for explaining, dark matter. It has the so-called LSP, lightest supersymmetric particle, which could be a dark matter candidate. So this is why a lot of people are interested in finding out or discovering a supersymmetric particle, because it could also not just, have us discover a new particle, but also solve another sort of not yet understood question about our universe. So that's one category. The other category is, sort of broadly speaking, what are called exotic models, and there are a whole slew of them, and many of them predict, for example, sort of you could call them, brothers, sisters, cousins of the standard model particles. So, for example, there is a standard model particle called the W boson. An exotic model predicts that there is another particle which is similar in many ways to the W, but it is much more heavy.
Is this the W prime?
It's the W prime,
it is? Okay.
absolutely.
All
It's the
right,
W
all
prime.
right.
So this is my favorite particle, the one that
your pet particle.
my pet particle. I have been searching for it, and I'm continuing to sort of search for it.
You hit the right time, right?
Yes, and so with this increase in energy as we go into run 2, it really allows us access to much more heavy W prime particles than we've ever had access to. And we can look at the W prime particle not just decaying in one way, but decaying in many ways. Because again, we don't know that in this new physics, which may be correct, that it decays in a certain way. So what we try to do is we try to cover all our tracks and really look for it decaying in all sorts of possible ways. And so that's been one of my focuses, is looking for such a particle. And then there is another similar particle, which again is very well motivated theoretically, is partner to the top quark. Now, we have 6 quarks in the standard model: up, down, strange bottom, strange charm, top, bottom, or
cleverly
truth
named.
beauty. Yes, very nicely named. So the heaviest of this is the top quark. Now, the top quark is very special because not just that it's the heaviest, it's about 174 GeV, it's a lot heavier than the other quarks. It's in fact the heaviest particle that we've seen because it's 174 GeV. The Higgs is 125. Now, why is the top quark so heavy? Okay, perhaps once we understand fully the Higgs and its properties, we may be able to understand that. But the fact that it's heavy leads us to think that if there is a new heavy particle out there, there is a good chance it may decay to a top particle. It may either decay to a top, or that there may be an exotic partner to the top. So therefore, searchers...
Another one.
Yes, it's called a top partner. It's called a top partner or T prime.
Yeah.
Just like you have the W prime,
yes,
we
I
have
see.
something called a T prime. It's often called T prime, a top partner. And therefore, you could have a heavy top partner which has some properties that are common to the top quark and some which may be different. So that's, again, one of those things that I have been searching for and I'm hoping might turn up in the data.
Yes. Is there anything else that they sort of anticipate in this new reboot, in the 2015 reboot?
I mean,
that I'm sure they're looking for all kinds of things. So dark matter, supersymmetry, particle, maybe variants of Higgs, or that's sort of
that's right.
Cousins, uncles, and things
yes,
like
exactly.
that. Right.
So the standard model Higgs is this neutral particle. There are other models which, for example, predict that the Higgs might have a charge. There might be a charge +1 or -1. And so a lot of interesting studies and research projects are going on which are designed at figuring out if perhaps what we might see might be a charged Higgs. Supersymmetry itself predicts that there are additional Higgses. And so it may be what we have seen, even if it turns out as a standard model Higgs, is fine because these additional Higgses have yet to be discovered.
I see. So there are all kinds of these things out there. We keep bumping into more and more particles all the time, but in this case it's all very exciting. Okay, let's go to your research, specifically the areas you've already mentioned this. I want to make sure we cover the exotica stuff too. But so you have several interests that you're in a perfect position now to explore. Tell us about it.
Right. So my main focus has been looking for these W prime and top partner-like particles. Part of that, and somewhat linked to my trigger work, myself, along with a few other people, came up with this idea of what we called the Exotica Hotline.
Yes,
okay, it has
I saw that.
Very interesting name, or interesting, you may say.
You may get calls that you
yes,
didn't
we do not
expect.
have a 1-800 number. Okay. Now, what we do have is, that as soon as, when the trigger selects these events, they get written and then people analyze them later on. What we do is, as part of that, we create a very small subset of events which we promptly analyze. Literally hours,
okay.
Hours of data taking.
Right.
And this is what we call like the express stream. This is the express data coming out as we speak. And what we did was, as part of this express stream, we came up with certain specialized requirements. That is, if suppose there was a W prime particle there, it would decay into an electron, for example, and this electron would be 1 TeV, 2 TeV. So we wrote some algorithms which would, in this express stream data, look for these W primes, Z primes, etc., such that we would know immediately within hours of data taking that we are starting to see something. And then we can really, get our act together.
Yeah, I was going to say you'd be focused.
And be focused. And so we wouldn't wait because since we're collecting so much data, analyzing it takes time.
That's what I understand.
And so this is just a parallel path where we look at a subset, but a subset with extreme characteristics, which we expect that these heavy particles will have.
It seems an advantage that it's a small group entirely focused on this. Is it?
I mean, yes, to begin with, because you have to think of what the ideas are. It's sort of it's also, for me, it was really nice because it was a nice connection between my searches for exotic particles and my trigger work, because it sort of brought both of them together. What we're of course trying to encourage is that the more people we have looking at this, the more chances are that we will cover everything. So we are, now that it's we understand it and it's worked out very well in run 1, we are extending it to run 2. We hope that more people will join this effort to sort of try and make sure we get the new physics as soon as it's there.
Right. Now, in this time, although you've got this experience from 2012, you're veterans now and so on, but this sounds like it could be really new, really unexpected at this energy. But you've pointed out that it takes a long time to scrutinize this data. That's after all this selection, all the trigger and stuff. Do you think it will work faster? It took a long while to confirm the Higgs, for example. They were very careful. What do you expect in terms of confirming, finding and confirming?
So, I mean, I think, firstly, there is always some amount of time you need to take to calibrate, align your detector. It's very easy to create new physics out of miscalibration. If you miscalibrate something, you see a spike, and you might get excited, and then you look more closely, and you see that's this faulty electronics firing at random. And it has happened numerous times, numerous experiments. In fact, it's almost a given that it will happen.
Exactly, but you know.
We know, and this is actually where the Exotica hotline was very useful in Run 1, because we would start seeing what looked like potentially interesting events, and then you find out it's a problem in the detector that needs to be fixed. So we have to first calibrate, make sure we understand our detectors, and then as we start looking at the data more closely, if it's a discovery, for example, if any of these new exotic particles are just around the corner, they should appear right away. Because it's just as this big jump in energy gives us this huge boost. So we wouldn't need to wait for years and years for this. So new heavy particles should appear in the first couple of years of data taking, is at least or what I hope. And of course, in the time from when you start seeing it to when you're ready to go out in public to claim a discovery is a little bit, because we want to make sure that we're not making a mistake.
And after the media experience in the past.
Exactly. And so it's very, very, very important for us to be careful. So unless we've had multiple analysis teams looking at the same data, coming out with the same conclusion, we wouldn't, just because two people saw something. We wouldn't. So any analysis, especially any high profile analysis, for it to be made public essentially goes through a very rigorous process through the experiment, where it is vetted by essentially a large fraction of the experiment, and when only everybody is on board do we say it's okay to make it public. So that's where sometimes the time goes, not in seeing the events, but actually making sure you're not making a mistake, everything is as exactly what it should be, and doing billions of cross-checks. And so this is where, if it was a strange new particle, you could have more other kinds of new physics. For example, standard model has certain predictions for rates of certain processes. And there are some processes which are very rare, which have very low rates. Now, there could be a new physics model which predicts an enhancement in this rate. But in order to actually see that, you need to collect lots and lots of data to be at that level where you could be potentially seeing if there is a discrepancy in this very low rate process. So for that, you need years. You cannot just say it at startup. So there are different kinds of physics we'll be doing, or concentrating rather, at startup, versus what we'll continue to do in parallel and what we will do, say, 5 or 10 years after startup.
Right. You are, I'm sure, a really fine professor as well. Are students very encouraged in this time? I can't imagine a better time to be in joining this field.
No, I mean, I think this is an amazing time. I know for example, for our graduate students, they are completely, I mean, we have already had a number of students start, coming to BU because they want to be part of this LHCFS. So that is definitely something that's on their mind. But not just that. For example, right now, I'm actually teaching electricity and magnetism to a large group of engineers. And I use a lot of my LHC work in my sort of lecture material, because the point is we are making use of electricity and magnetism, and the LHC is an engineering marvel. So I tell them that, look, your peers have created this magnificent machine, so you can do that.
That's true. They can pat themselves on the head.
And you can do that too if you pass my course.
Exactly. First, pass that course.
But I can see that in their excitement. They just, they might be taking notes, and then when I start mentioning the LHC, they're looking up. and
right.
it catches their attention.
Absolutely, and that's very good of you to remind them that engineers built this thing, and it's amazing. It's just an astounding accomplishment. Dr. Bose, you have also tried to promote funding for science. I think you're involved at Fermilab with something like that. Would you please tell us about it, because this is important for this organization to support funding for science?
Yes, I mean that is a very, very big deal, because as you're seeing, what we have are these amazing detectors and accelerators, but they are very, very complicated. They need large numbers of people to make them work. If we don't have these people, these machines will not work. Now, so what I'm doing, I'm part of the Fermilab Users Executive Committee, and part of our job is to do outreach, to tell people the kind of work we do, what its benefits to society are, and also to, for example, go to Washington, D.C. and talk with people in Congress and the Senate, and again, tell them, look, this is the work we are doing. And there are two things.
And this is international.
And this is international. This is huge, collaborations worldwide. There is something we are doing in fundamental science which is helping us understand nature. And, we know for a fact that what we have today, or what is coming out of our work today, may very well launch a revolution 100 years ago, 100 years from now. I mean, for example, what we are seeing, what is common now, semiconductors, superconductors, all of this work came out of various particle physics experiments, in the last 100 years. Not to mention, there are lots of other sort of, benefits to society. We have accelerators which are being used for medicine, for cancer treatment.
Right, yeah.
We have, MRI scans, PET.
Yes.
All of this comes from basic fundamental science.
Right.
And the World Wide Web, without which we would not exist today, literally, is a side benefit of the work at CERN.
Right.
So all of this has come out of the fact of fundamental science, and so the fact that we need this to happen means we need support for this, funding for this, and that's why having the public on board with what we are doing and its value to society, to us, the world, as a community in general, is very important in order to get support from the funding sources.
Is there a kind of unity of support in, say, the European, other nations? Many nations are involved in this project at CERN. Is there less difficulty getting the funding in other countries, or?
I think it depends probably from country to country, and some countries are doing better than others, but they do tend to work. For example, a lot of the European countries, because they're part of the CERN Council, they do have some sort of a system which sort of brings it together. So we're a little outside that.
Right.
It's a challenging time from everywhere in the world, but certainly some countries are doing better. Japan, for example, is moving forward very soon. Perhaps in the next year or so, with a new collider.
Yes.
And that would be the next sort of step, and they seem to be doing well. China is moving ahead.
Yes, everybody wants to have a collider. Right, be nice to just put it all in one place, rather not Japan.
So I think that's what we are realizing, that the scales of these experiments are so large that we can't possibly have one in each country.
Right.
So these will have to be international collaborations. So we will need to collaborate with each other. We can have something big here, people come here. We have something big in Europe, for example, at CERN, we go there, and it's a collaboration.
Right. One more thing. Where do you see Fermilab going now? What are they going to concentrate on neutrino?
Yes. That's the current plan. The idea is that Fermilab might be the location for this big neutrino experiment that will start up in the next 10 to 20 years, and that would be the central place then that people from all over the world would then come to Fermilab to work on neutrinos at Fermilab.
There's a great sentimental feeling about Fermilab here, I think.
Yes,
so.
Definitely. I mean, I myself, I did my graduate work at Fermilab, and so I really wanted to do well. And unless there is a very big, active, experiment there, for which we need support. So we need support
Exactly.
from the funding agencies to be able to have that work and work well, meaning we don't want to descope it and make it an experiment which can do half of what its goal is.
Exactly. Well, I hope that the public will stand by this whole project. It's certainly garnered a huge interest. The film Particle Fever was very popular despite limited distribution and so on. So I wish you all the very best in this wonderful time for your career. Thank you very much for joining us.
Well, thank you very much for having me. It's been a pleasure talking to you.
Okay, good.
I grew up in India, a number of places in India actually, because my family moved around. We were in Calcutta, in Delhi, in Bhopal. So I did my early education in India. I went to college in Delhi, Delhi University, St. Stephen's College, and then I got a scholarship to go to Cambridge University in England for my undergraduate. So I went there, did my physics undergraduate degree from there, and then came to the US, 1998, for grad school at Columbia. My father is a political scientist, my mother did literature, so there was nobody around me doing physics. There was a lot of emphasis in science education, in engineering, medicine. All of these had sort of equal importance, and in fact as children we were sort of urged to go into these fields, mainly from the point of view that it's a developing country and these are going to give you good jobs, once you go more senior. So it was actually in Cambridge in England when I did an undergraduate thesis, and this was at that time an experiment that was at CERN. This was a precursor to the LHC. This was the Opal experiment. And it was when I was doing that project that I was thrown into this world of particle physics. And at the same time, in the US, a very exciting discovery happened at the Fermilab Tevatron. This was the discovery of the top quark. This was 1994. So I knew, this was 1993, I'm back in England, and I knew I have to go to the US because I want to be part of that team that discovered the top quark. And I came here. I did a small research project on the discovery of the top quark, and then got heavily involved since then. There are two main areas. I am currently serving as what's called the trigger coordinator of the CMS experiment, which means that I have to make sure that we collect data, the data that we want to use to discover new particles in physics in a way, because we collect lots and lots of data at the LHC. This is huge amounts, but how much of it is relevant for the kind of physics we want to do? That decision actually has to be made online, and I'm part of the team which does this. My other sort of main area working on the CMS experiment is to actually search for new exotic particles. We expect that the new run of the LHC should open up a floodgate, hopefully, of new particles, and I want to be there discovering them. So periodically when we were taking data, I was based at CERN for almost about a year and a half, then I came back here. Now I travel back and forth. Starting next year, as we get closer to the run, I'm going to go back there, and I'm going to be again based there for about a year and a half.